Okay, welcome everyone to the next session on NPTEL course assignment on engineering hydrology. In today's session, we are going to discuss the numericals as well as the conceptual type questions related to hydrological analysis, linear system theory, unit hydrograph, then direct runoff hydrograph. Then we will also look into S-Hydrograph, S-shape hydrograph. What is its importance, significance, and how we are using these concepts in the field scale. Kindly confirm whether this screen and audible is okay for you.
Yeah, it's visible and audible.
Okay, that's good. Okay, so today's first question is related to the shape of hydrograph. So the question here is, wait a minute, my writing pad is not working right now. Let me confirm. Wait a minute. It is working. Okay, now it's working now. Yeah. So the question here is, the shape of recession limb, that is the falling limb also, of the hydrograph depends on. So I guess this question was already covered in the previous sections, but just for the revision, you can answer this. What could be the factors that are influencing the shape of recession limb?
It's basin as well as storm.
Okay, you are saying basin as well as a storm. Anyone other?
Basin characteristics only.
Yes. Okay. So basin characteristic. Ashish, basin characteristics will only influence this area, because when we are talking about the rising part, so it is all about the discharge. Okay, whatever the direct runoff it is coming in the catchment at the outlet, so that is why it is generating a highest peak because of the storm. So in this case, both the parameters like basin characteristics, that is size, shape, topography, and then coming to the storm, that is duration of the rainfall, then intensity of the rainfall, they both of these parameters will be influencing this rising part. But if we are talking about the recession, then definitely only the basin characteristics, because now the storm has already stopped. Okay,
Okay.
so remaining part, whatever the which have been stored in the subsurface zone, it will be coming out in the form of base flow now. Okay, and that's why you are getting somewhat this base flow contribution as well as the remaining water that have been maybe stored in the depression, or maybe in like in other form of abstraction or interception. It will be coming now. Moving ahead. Okay, just for your information, it is mentioned that catchment characteristics will only have the effect. And what could be the characteristics? So shape, size, slope, drainage density, topography, and geology. It has been mentioned that if we are having elongated catchment, then definitely we will be having lesser peak as compared to this nearly circular shape of catchment. Okay, in case of nearly circular shape of catchment, peak will be much more higher as compared to elongated one, and in other scenario duration will be low, duration will be less as compared to the elongated one. Okay, now the next question here is related to unit hydrograph theory. So it is now asking about what are the assumptions that are involved while we are uh, like plotting the unit hydrograph. Okay, so it is asking about the assumption. So I hope you already gone through this. So tell me what could be the assumptions. I guess two is major assumptions are involved in this case while we are making unit hydrograph. Anything? Anyone answering to this question?
Time invariance and linear response.
Yes, ma'am, you are right. So this question, option is right. D1. So here we can see in the explanation part. So major assumptions involved in case of unit hydrograph. So first one is linear hypothesis, which is accounting the proportionality that uh, if certain amount of input is coming, that it will be directly converted into a output. So you can see here it is also mentioned that superposition principle will also act in a similar fashion. So that means if input I1 is coming plus input I2 is also coming, then definitely it will be converted into output 1 plus output 2. So this is a superposition. Then accordingly intensity as well as the duration will also have the distribution. We have to adjust those values. Then the next one is time invariance. So that means in the entire annual water year, like I am just talking about January to, you can say, December. So whatever the unit hydrograph we are getting, it will not have any effect like in the entire water year. Like you can say January, February, then coming to, like, I'm just highlighting the fact that yes, there may be a pre-monsoon season, there may be a monsoon season also, right? But yes, they won't have influence in the while we are plotting the unit hydrograph. So this is an assumption involved in this case. So time invariance has this meaning. So you can see direct runoff response to a given ER in the catchment is time invariant. That means it is not changing, it is having a same value. Like in the next line it is mentioned that DRH for a given ER, that is ER in the sense that is effective rainfall in the catchment, will always remain same irrespective of when it occurs. That is, it is just mentioning about the time. Okay, so it is always remains same. Then there are some more assumption that is related to space invariance of effective rainfall. Then you can see DRH response from the catchment represent the unchanging characteristics of the catchment. And two more assumptions that are majorly you can see 1 and 2. These are the major assumptions that carried out when we are going through a unit hydrograph. Then some more related, not a specific one, but yes, we have to keep in mind that yes, UH theory assumes that there is no storage component. Okay, whatever input is coming, it is converted directly into an output. Now going to the next question here. So So the question here is the correct sequence of the following step involved in arriving at the unit hydrograph. So I hope you already went through some of the problems related to unit hydrograph where you have encountered a step, okay, that how we arriving at the unit hydrograph. Have you done any kind of have you gone through any kind of numericals related to this? Anyone can reply?
No, I didn't go through it.
Okay, maybe in the lectures you might have like got one or two numericals related to this. So here, what will be the sequence? So firstly, just I want to know that how you can arrive at unit hydrograph. So unit hydrograph in the sense what? Firstly, tell me what you understand by unit hydrograph. Firstly, tell me the definition. Like there should be some understanding from this word unit hydrograph. So what do you understand by this? Firstly, tell me this. What you understand by unit hydrograph?
It's the hydrograph arrived on applying unit 1 centimeter rainfall over applied uniformly over the basin at a uniform rate
Yes.
during a specified period of time.
Yes. So it is asking, it is saying that due duration of rainfall is maybe there. So yes, ma'am, you are right. So 1 centimeter of rainfall occurring uniformly over the region for D duration. Okay, and that will be giving you a direct runoff hydrograph. So DRH will be there. Okay, direct runoff hydrograph. So DRH, it is saying that DRH, but whenever we are getting the hydrograph, so it is having the total runoff hydrograph you may be getting. Okay, it won't be a direct runoff. So just I want to mention that if I am plotting the total runoff hydrograph, then you are getting a graph like this. So it is also including the base flow. Okay, so in order to get the unit hydrograph, firstly what should be the first step? So it should be like, firstly you have to remove this base flow first. So first step will be you have to remove the base flow and then start plotting this graph. So now when I will remove this part, this whatever the hydrograph I am getting, so it will be plotted now like this after subtracting some of this value. Okay, this will be Q only, base flow will be in terms of discharge only. Now it has been subtracted. Now what you are having again a Q versus T plot. And what you want unit hydrograph, that means 1 centimeter of effective rainfall plot you want. But have you think about if I am plotting a generalized hydrograph, that is a total storm hydrograph, that is a total runoff hydrograph I used to say. So if I am saying that total storm hydrograph, or not a storm, that will be a runoff, total runoff hydrograph. So this will be generated from the total storm only. So if I am saying that if there is a catchment, then total amount of rainfall is coming here 12 centimeter. So now for 12 centimeter you have got this graph. This is for 12 centimeter. But what you want to plot 1 centimeter, that is a unit hydrograph. So what should you do? You have to divide this, whatever the values you are getting, you have to divide this with 12. Then only you will achieve to 1 centimeter. So for that case, firstly you have to separate the base flow. Then what you have to do? You have to compute the surface runoff in volume. taking the area under this graph, you can compute the volume. Okay, now you got the volume. Now then again we have to compute the surface runoff depth. That means what? Depth in the sense what? Depth in the sense,
Divided by the area of the.
yes, right, volume y divided by area. We will be getting the this depth, but this depth will be for what? This depth will be for the entire catchment. Now the fourth step that is he mentioned here, divide the surface runoff ordinates by the depth of runoff. Whatever the Q values we were getting, we have to divide this by depth of the runoff. Okay, and then we will get the unit hydrograph. So here you will see this option A. Okay, 3, then 2, then 1. Actually this entire procedure you will get more understanding while we are solving the problem. We will go through some of the problem, then you will ultimately you will get what should be the procedure for this. Okay, I am moving ahead now. Okay, so just for the information, it is mentioned here that if we are talking about the direct runoff hydrograph, then firstly volume of the direct runoff should be determined by estimating the area under DRH curve. Then volume of direct runoff should be divided by the drainage area in order to compute the depth of runoff. Then this must be equivalent to effective rainfall of the storm. That should be just I was mentioning 12 centimeter. So whatever the depth of runoff you will be getting, it will be equivalent to 12 centimeter. And now what you have to do, you have to, in order to get the 1 centimeter of effective rainfall, you have to divide this 12 by whatever the discharge value we are getting, we have to divide it by 12. Then we will get the 1 centimeter of ER. We will get the values for 1 centimeter. So whatever the division we are taking, this is coming under the principle of proportionality. That is coming under linear response. We just discussed one of the assumption. Now here again the question related to unit hydrograph. It is saying that if we are having 2R unit hydrograph, okay, and they are staggered by 2 hours, it means it may be lagged by 2 hours, and added graphically the resulting hydrograph will be. Okay, so it is saying like graph is plotted like this. You can, I'm just plotting here. Okay, so this is for 2 hour duration. Now again you can say if 2 are staggered by 2 hours and added graphically. So if I make it if I lag this entire unit hydrograph by 2 hours, in the next step I am making. So now again I am lagging this. Now I will be reaching up to how much? What will be the duration here? If I am lagging this unit hydrograph by 2 hours, then what will be the duration now?
4 hours.
4 hours. That's good. But now you have to tell me that if I am, what it is saying that we have to add graphically. Now we have to add the values graphically. So if I will be adding this graph graphically, then I will be getting somewhat not up to this peak, but yes, it will be going like this. Just let me erase this first. Wait a minute. Okay. So what I was just mentioning is that I'm having this hydrograph, then I'm lagging it again by 2 hours. Now I just like I was asked to add this graphically, so I'm adding it graphically now. So this will be the graph now. Okay, so if I'm saying that this is UH1, then this is UH2, and this is 0, then this is 2 hours, then again this will be what? This will be 4 hours. Now you know that this UH1 was having 1 centimeter of effective rainfall, right? Am I right or wrong?
Yes.
Okay, and then again I just lagged it by 2 hours, so definitely it will again have 1 centimeter of effective rainfall. And now it is asking that we have to find out the resulting hydrograph. So resulting will be adding up both the unit hydrograph now. So if you add up both the unit hydrograph, you will be getting 4 hour of duration for this unit hydrograph, graph. At the same time, what will be the effective rainfall value here in total? It will be 1 plus 1, right? It will be 2
Yeah, 2.
centimeters, right? Am I right or wrong?
Yes.
Okay, good. So just I want to know that, tell me which assumption is working here. This is also seems to be interesting to know, right? Which assumption?
Time invariance.
No, ma'am.
No.
It is
Principle
related
of
to,
superposition.
yes, principle of superposition, right? Yes, principle of superposition. Superposition. Just I just mentioned that I1 plus I2 will be equal to Q1 plus Q2. But yes, if I am adding this, then definitely there should be an increase in it will be added cumulatively. Resulting value will be more. So that's why you should have idea that now we will have 4 hour unit hydrograph with 2 centimeter of runoff, right? Okay, got it.
Yes.
Yes, yes. Thank you.
Okay, just for your information, it is mentioned that yes, linear response we were talking about, that was assumption. So in that case, principle of superposition, that is the principle used for deriving such kind of situation. So if we have two solutions like f1q, f2q on the system are added, then resulting function f1q plus f2q is also a solution of the linear system. So you can see there is one graph in different colors, and then it is getting added up, so we are coming up with f1q plus f2q. Okay, and that's why we are getting 4 hour unit hydrograph with 2 centimeter runoff. Okay, come to the next question here now. So it is saying that over a period of time, a watershed got transformed from rural to urban. So I guess it is asking about the urbanization, effect of urbanization. Yes, the effect of urbanization on the storm runoff hydrograph from the watershed is 2. I guess we already covered this question in the previous session as well. But yes, if you have if you still remember it, you should definitely tell this answer. It will be nice to know. It is saying that effect of urbanization. Okay, anyone? Ashish?
Increase the volume of runoff.
Okay, so you
Oh,
are
I'm sorry, that
saying,
is not, no, no, that is not available as option. It should uh, decrease the time
Yeah,
base.
decrease the time base, I think.
okay, okay, so you are saying decrease the time base. Yes, of course you are right. If we will be having a rural kind of area, then definitely there should be more abstraction or maybe interception losses may be there. Okay, so you may be getting a graph like this, but yes, in that case duration will be more. Okay, but when if that entire area is now getting urbanized, we are adding concrete, more concrete type of structures, or maybe artificial structure, then definitely there will be more possibility that whatever the rainfall it is falling in the region, it is getting a higher peak value, or at a shorter duration, right? So D will be small, and we will be having more chances of flooding, right? Flooding or maybe waterlogging problem may be the situation. Okay. I guess do you if you are listening current news, day by day news, you may have already come across one of the problem, or maybe a water scarcity challenge that is happening in the Bangalore, right?
Mhm.
You have you come across, you heard that news or not?
Yes, yes, yes.
Yes, yes.
Yes, so groundwater table is depleting
Lowering.
continuously. Now they don't have water to survive, even for the daily use. Okay, so we should have understanding, and even I feel that if we are having a water logging or maybe a flooding kind of situation, definitely we should have some appropriate kind of structures. If we are definitely if we are urbanizing the area, so we should also install some kind of uh, tank kind of a structure in beneath the like beneath every building, I guess we can. And if there is a surplus amount of water it is coming, it can store, it should have some capacity that yes, we know that water in the monsoon season a certain amount of water will be coming in excess, we can store that amount, and we can in case of pre monsoon or maybe non monsoon season, we can utilize that water. But yes, now the problem is now more worse, getting worse. Yes, you already know the explanation, you already give the correct answer, so I don't think we should go through the explanation, you already know the things. Coming to the next question here, S curve hydrograph is the hydrograph. Now you have to explain what is the actual uh, assumption, or we can say the process for getting the S curve hydrograph. Anyone? Ashish, you also let me know at while we are going through the whatever the Bala Murugan is applying. You can add
Okay, okay.
summarizing the facts. Okay, because if I am stopping this presentation, then it is still wasting few minutes.
He says B is the right answer.
Okay, so you are saying that, or
Balamurgan is
okay,
saying that.
Bala Murugan is saying. Okay, that's good. So Bala Murugan, you are right. Yes, whenever we are talking about the S curve, so definitely DRH will be derived considering 1 centimeter, like that should be an intensity. Okay, intensity will be it will be having a uniformly distributed for an infinite duration in the catchment. Okay, uh, you already maybe knowing the things that yes, if we are plotting this S kind of curve, and here also the lagging principle works. So if I am lagging it here 2r, so you will again getting a S kind of curve, but yes, at one time, okay, these all values will get constant. Why? Because peak will be constant now. It won't be like whatever the peak value it will be having, it will remain constant. So most of the time you will be encountering a question related to S curve. So that is a equilibrium discharge. Okay, equilibrium discharge, or maybe you can say like that is a discharge where we now we are getting the constant value continuously. Okay, so you will be having like I guess there are one or two numericals in this session. We will discuss these questions related to equilibrium discharge using S curve. So yes, B option is correct. So just for your information, it has been mentioned here that DRH observed at the outlet of catchment when it is subjected to an effective rainfall intensity. This is an important thing. In case of unit hydrograph, we are saying that this is an effective rainfall only. 1 centimeter of effective rainfall is happening. But in the here, you will be having a rainfall intensity, effective rainfall intensity of 1 by D duration. 1 by D centimeter per hour for an infinite period. Okay. So here further there are some more points have been added here. So now you can see that how they are deriving this S curve. So now this example is basically this picture is demonstrating the fact that using the unit hydrograph, multiple unit hydrograph, we can derive S curve also. So you will have some questions where adding to if we are superimposing unit hydrograph, how we can derive the S curve. So we will discuss in the next session related to these problems. But here it is also mentioned that how we can compute, we can get the effective rainfall for entire S curve. So this is a procedure for this. How we can get this entire what are the values, or maybe how it is varying with the discharge is varying with the time, we can get using this procedure. We will discuss in the next question, next session. Now the next question here is stochastic hydrologic model is based on. So here it is mentioned space, time, randomness. So firstly, before going to this, I just want to know, do you have any idea about hydrologic model? Hydrologic model, and what type of model you know, like any kind of model have you used or encountered, or maybe you have studied, any idea related to this?
There is
Rainfall runoff model.
yeah.
Yes, that's good. Rainfall runoff model, it is also a hydrologic model. Rainfall runoff model. So here rainfall is an input parameter, you can say. So here we are giving an input to a system. That is important. This is a system. What is system? System is just a, you can take example of catchment. So catchment, entire catchment is our system. Now rainfall is coming here. So catchment, you can now have some idea that why we are saying the system, because there are many parameters which are the deriving force for generating the runoff, I should say. That is an output. I am talking about the output. So output in the sense we will be getting a runoff now. But this runoff will be influenced by the system properties, catchment properties, right? Catchment properties in the sense what? That could be an aquifer parameters. Aquifer parameters may be there. Maybe what are the properties we have for the stream? I'm just saying that I know the slope of the river, right? Slope of the river will also have influence in generating the runoff, right? Length of the river will also have effect. Width also will have effect. Then aquifer parameters in the sense what I am just saying is that what is the depth of soil present in that area, what type of soil is present in that area, what kind of LULC pattern is there in that area. So in cumulatively I can add that this is a system. So catchment is entirely a system. Okay, so in order to predict the runoff from rainfall input we should have some this model kind of thing, okay, where we can give the input rainfall, and we will also define the parameters, system parameters, and then ultimately we can compute the Q value. Okay, so I guess you all remember SCS-CN curve method, right? SCS-CN curve method. So this is also one of the hydrologic model through which this is also like rainfall runoff model only. Okay, but what I just want to mention here is that when we are saying that we have a catchment, okay, now I'm just saying rainfall you got, okay, also you have to define the system parameters. That is also important, because once you got the idea of system, then only you can compute the runoff. So for that case, this entire area, how is it behaving or how we want the response, okay, we have to divide this, like we have to take some assumption that how we want this value. Like if I am saying that yes, in entire region only this part of area is getting the rainfall and generating the runoff, but this area is not having any influence. So how we can we can incorporate this? Okay, maybe there may be a case that yes, intensity may be high in this area but not in this area. So in order to associate the spatial as well as the temporal variability of input parameters or the catchment characteristics, we should have some assumption that how we want the system to respond. Do we want a single value in the sense what, all whatever the value we are getting, whatever the rainfall we are getting, it will give a direct single value at the output. This is an output. But if I will divide this area in some discretization, okay, and now we want to compute the output, so it will have some more accuracy while we are getting the runoff in the earlier case. Now in the similar fashion, there could be some probability related to input parameters also. Why I am saying this? Because if I am giving a rainfall data, then definitely there should be someone who is recording this data also, or maybe there may be a chance that whatever the rainfall is happening, it may be recorded with some error. So in that case randomness will be there, okay, probability will be there, uncertainty will be there. So to incorporate these things, randomness will also be an important part. So space, time and randomness, these three parameters determine the stochastic hydrologic model behavior. Okay, so randomness is important because it is defining the probability in this case, probability associated in computing the runoff due to the effect of some uncertainties which have been incorporated in the input as well. When we are giving the input, uncertainty was there, errors are there, and now we are getting a change value. So you can see here, stochastic model has the output that are least partial random. That means definitely there is a randomness. One might say that deterministic models make forecast while stochastic model make predictions. So deterministic, what I was just mentioning here, assumption, like if I am taking this entire catchment as a single lumped like you can say a single unit. Okay, what there is no change in the catchment characteristics. If LULC here is agriculture, then I am saying that entire region is having agriculture only. There is no change in the LULC pattern. Also, soil is having the same value across all the region. So that in that case, if we are predicting the output, it will be considered as a deterministic model. It will be considered as a lumped model. Lumped is just a part of deterministic model only. Deterministic model can be divided into two parts, lumped as well as the other one is distributed. Distributed model is also there. So what just I mentioned in the previous diagram. So if we divide this entire area in order to incorporate the spatial variability in the region, spatial as well as component variability, it will be coming under the distributed hydrologic model. Okay, both keep in mind that lumped as well as distributed, they both are considered as a deterministic model because they are giving the reasonable value. There is no randomness involved because just we are dividing. This is depending on the accuracy we want in our result, we want in our output. So based on this we have to select the model. Now if we are saying that stochastic model make predictions, so definitely if we say that climate predictions are happening day by day, climate predictions are there. Why I'm just saying that stochastic model is there? Because every climate prediction come up with certain degree of uncertainty. No one can say that yes, I just predicted that that in the region I'm receiving only 120 centimeter of rainfall. Now it will be, if any forecast is happening and they are saying that 1200 centimeter will be there, so definitely it won't come because they are just adding the word prediction. So prediction will be always come up with certain degree of uncertainty. So this uncertainty will be added, like it is represented by the word randomness. Okay, now you can see the picture also here. This picture you can see that how the Q is like having the probabilistic distribution. This is a kind of Gumbel distribution, you can say. This is a like a probability distribution type of curve, Gumbel distribution. Okay, Gumbel or I guess not a Gumbel. It should be a Gaussian distribution.
Gaussian distribution.
Yes, right. So it should be a Gaussian distribution now. Okay. So here it is. There is an example. Most daily precipitation models, okay, are stochastic. It is mentioned daily precipitation because there should be a more uncertainty in this case while we are recording this. Okay, moving to the next question here is, in a linear reservoir. So have you go through some this concept linear reservoir? What we understand by linear reservoir? I guess this is the part of, I guess, routing. Have you gone through this? Linear reservoir. Anyone? Okay, I guess while we will be discussing the problems related to flood routing, we will have this concept linear reservoir, because linear reservoir is basically a word that defines the storage. Okay, storage. So that means that if Q is coming, so how it will influence the storage. Linear reservoir, you can say, you can just have, just from the word itself you can have idea that yes, it is asking about the some kind of reservoir, then definitely there will be some input it is coming and there will be some storage will be there and then Q will be generated. So now why they are saying that linear reservoir? Because there is they are assuming that outflow will be like it will be having the linear variation with the storage. Okay, so this is the thing it is mentioned in this assumption while we are discussing the linear reservoir. Okay. So here linear reservoir, you can see a reservoir in which storage is directly proportional to the discharge. Okay, so that is the outflow. So if S is directly proportional to Q, that is outflow, then if we add some proportionality constant in order to remove the proportionality, so S will be S equal to KQ. We can write it like this. So this element is used to provide the attenuation to a flood wave. Just I mentioned that this is a part of flood routing. So basically why this word attenuation is mentioned here, because while we are plotting the like flood hydrograph kind of thing, so if I'm saying that I'm getting a Q peak, okay, like before dam, I can say, okay, before dam or reservoir. Now the reservoir has been constructed and flow have been controlled now, because there will be some storage will happening here. And now if I plot again a flow this hydrograph, then you will be having idea that yes, peak will now be it will be controlled now. It will have some lower value, right? So if I'm saying that this is 1, this is 2, so you can I'm just drawing a line, so difference in the peak you can see. Okay, so whatever the difference you are observing just because of the due to the presence of reservoir, so that is considered as a attenuation. So this is called part of attenuation. Okay, we will discuss there are some numericals also related to this. We will discuss it. Is it clear to everyone?
Yes.
Okay. Okay, so there is one more question. Unit step response function at a time t can be obtained by. Okay, so it is saying unit step response function. So before going to this, I just want to mention one line that you may have studied instantaneous unit hydrograph.
Yes.
So in order to have some idea related to instantaneous unit hydrograph, there have been some functions which have been utilized. So among those functions, you may have studied unit step response function. Then there is a impulse response function is there. Okay, so these kind of functions are helpful in order to reach and derive the instantaneous unit hydrograph. So I guess you may have studied in your lectures that how we can represent unit step response function with respect to it is mentioned that how it is all about, this question is all about a relation. Okay, so it is asking about a relation in terms of what, differentiation or integral, and with what, these are the response function you may be seeing. Impulse is there, pulse response function is there, impulse for. So with pulse and impulse there should be some relation with unit step response function. Any idea to this?
We're differentiating pulse response function.
Okay, so differentiating the pulse response
And
function at that time. Okay, anyone, any other, anyone else?
Balamurugan says it's C, integrating the impulse response function.
Ah, yes, right, Balamurugan, you are right. So integrating the impulse response function up to that time, we will see in the explanation part. Okay, so firstly, before going to the option what is right or wrong, firstly go through this impulse response function. So what it does mean, so if a system receive a unit impulse at a time tau, you can say, okay, then the response of the system at a later time, if we are saying, then this is the representation u, it will get lagged. Okay, unit impulse, it will getting lagged now. Unit impulse in the sense, you can say there could be a impulse in the sense what, there should be it should be having a any kind of input parameter that is having a effect in the system. Okay, if it is saying unit impulse, then definitely you can assume that yes, unit precipitation or unit intensity, precipitation intensity is happening in the system. Okay, so now if I'm saying that there is some time lag of t, then how that impulse will be derived? So you can see t minus tau. Okay, so in this case you can say there is a one like bar kind of thing, a column is there which is representing a unit impulse. Then if we lag it, we are getting a variation now with the variation of time. If it is saying t, so definitely it will be ranging from 0 to tau now. So between 0 to tau it will have variation like this. Coming to the step response function, so unit this step response function is basically derived when we are giving the unit step input. Okay, and we are giving unit step, and then we are taking cumulatively, like we are integrating it, we are adding, making it cumulatively, and we are getting the unit step response function. So there is one convolution integral for representing this. Okay, and now after applying the convolution integral for this step response function, so now we have both relations. Okay, we got understanding about impulse response function. So it will be represented by u t minus tau. You can imagine at any kind of parameter. Okay, input parameter in the catchment. And now you also got an idea of step response. So the difference is what? You can see that we are just taking a cumulative value of this. So in order to add this cumulation, so integral value have been placed here. Okay, and now how now they, if you talk about the relation between impulse as well as the step response function, there is one assumption that has been taken here. So in order to get the value, t minus tau have been assumed as L, then we are taking the differential in order to take the integral value, and accordingly we are changing the tau value. So there is final this expression come up. Okay, so gt is here is what? Gt is representing step response function. And what about the integral part, that is ul? So ul was impulse response. Here L is what? It is representing t minus tau. So now the final relation have been derived. Unit response function gt at a time t will be equal to integral of the impulse response function up to that time. Okay. Okay, now the question here is about a numerical problem. So I want everyone to kindly go through the problem and try to get the answer. Okay, the question here is the peak of 5 hour unit hydrograph of a catchment is 150 meter cube per second. The question here is the peak of, if I'm I'm plotting 10-hour unit hydrograph in the same catchment, what will be its peak? QP it is asking. Keep in mind that catchment is same. So in first case it is saying that 5-hour unit hydrograph have been plotted, and what we are getting a peak value of somewhat 150 meter cube per second. And now in the same catchment we are saying that we are plotting a 10-hour unit hydrograph now, and we want to know the idea of QP. Okay, so you can plot this hydrograph. So it is saying that 5-hour duration, so 5-hour will be like this. Okay, and one more thing will be there, that this will be a 1 centimeter of excess rainfall. Okay, and from this you should have idea that yes, this is a peak value. Okay, so QP is what? QP is 150 meter cube per second.
Hmm.
Okay, now you have to come up with this. Tell me how we can approach QP. We have to find out for 10 hour.
So you have to. Balamurgan says that it is less than 150 meter cube per second.
Yes, he is
I
right.
too felt that. See,
Right.
I too thought.
Yes, yes, yes. So kindly tell me the approach, how you are getting less than 150 meter cube per second.
When the base period or the duration of the rainfall is more,
Yes.
um, um, the rainfall is distributed over a longer period, no?
Right,
So
right.
naturally the peak will
Yes,
be
peak will
less.
come down. Right, right. Yes. Okay, good. We will look into the explanation also. So with the increase of unit hydrograph duration, okay, 1 centimeter excess rainfall will occur in an increased period. Just ma'am mentioned here that duration will be increased. So what will happen? P coordinate of the unit hydrograph will decrease and the time base will increase. And that is why we will be getting a P coordinate of 10 hour unit hydrograph will be less than 150 meter cube per second. Any doubt till now?
No, it's clear.
Again, the question here is a 5-hour effective rainfall of 12 centimeter over the catchment produced a peak runoff of 600 meter cube per second. Again, in the same watershed, another 5-hour effective rainfall of 4 centimeter produces a peak flow of. So, if I will write given data, so in the first case we are having 5-hour unit hydrograph. Okay, 5-hour effective rainfall. Oh, okay, it is not a unit hydrograph, it is a 5-hour duration hydrograph having 12 centimeter of effective rainfall. So ER here is not 1, ER here is 12 centimeter. Okay, and further information is given here that QP is given. QP is 600 meter cube per second, right? And in the second case, catchment is same, so properties will be same.
Hmm.
So 5-hour of duration is same here, but rainfall, effective rainfall is changing. Effective rainfall is how much here is? Here 4 centimeter effective rainfall. Now it is asking about QP again. We want to compute QP. Any idea? Anyone getting answer, or maybe you can take your time.
12 by 5. It's equal to 600.
Anything going in your mind? How you can get this?
Trying to find this 2.4. 1 minute.
See,
1 minute. I'm calculating.
yeah. Calculate it and keep in mind that here one thing you mentioned, same watershed. That means area will be
Hmm.
constant. Okay,
So
that
1
is one of
centimeter
the
per
additional
hour equal
information.
to 600 by 2.4. 100 to about 2.4 is equal to 250 per hour into 50. So, we have 4 centimeter per into 50. It's 200.
Yes, it's 200, right? Let other also solve. If,
Yeah, he also solved Balamurugan. He says I think 200 also. Same.
okay, that's good. Ma'am, what about you?
Yeah. I just got 200 because is the properties are same, duration is same. Uh, so naturally, the effect is proportionately less. For 12, it is 600. It's one third of it, right?
Okay. Yes.
Is there any other approach different from that? Am I wrong?
Uh, I will see in the like you can see in the explanation. Okay.
Okay.
Yeah. So I guess there is nothing simple. Whatever the unitary method we are using, that is a simple only. So here we were having peak runoff of 600 meter cube per second for 12 centimeter of effective rainfall. So what we did, firstly we have computed the unit hydrograph. Okay. So unit hydrograph P coordinate in the sense what? UH. Firstly, keep in mind we are computing the UH. So definitely we have to divide this entire value by 12 centimeter. Then only we will get about 1 centimeter. So for 1 centimeter, we are plotting the like we are targeting to get the value, this much of value. Okay, this is the P coordinate. P coordinate, right? So if we are dividing 600 by 12, then we are getting 50 meter cube per second. Somewhat. Don't go through this unit here till now. Only are you getting this ratio for 50? 12 5s are 60. Yes, right, 50. Now for 4 centimeter of effective rainfall, so we got the idea about unit hydrograph, right? Means that is 1 centimeter. For 1 centimeter of effective rainfall, what is the P coordinate? Firstly we have to target P coordinate. You all are right that just we know that proportionality is working here. Okay, so proportionality we already studied in the linear response, right? So there are two things that we already focused. Okay, so first one was what? Proportionality. Okay, proportionality was there. Then again the second one was superposition. Okay, so these both these things were coming in the linear response assumption. So you are right that if you take direct proportional, we can also get this value. But yes, if you approach like this, firstly you have to go through and compute 1 centimeter of excess rainfall value. Okay, and then you can multiply whatever the value you are getting by 4 centimeter, like whatever the value it is asking. If it is saying that you have to compute for 8 centimeter of excess rainfall, then you can multiply it. So this is a thing, this is the approach you can follow. Else your way also correct. Okay, now moving to the next question. So we have to compute equilibrium discharge. I mentioned in earlier discussion that at at one time this S curve will get constant if we keep adding the unit hydrograph. So now this is the equilibrium discharge it is asking. So I will represent it as QE. Okay. Additional information is that area of catchment is given 270 kilometers square. Then You also have idea of unit hydrograph. So duration is given, duration of the rainfall is given here is 3 hours. And then one more thing is that unit hydrograph is mentioned. So unit hydrograph in the sense what? We are having effective rainfall of 1 centimeter. So we also have this idea. Now what we want to compute? We want to compute equilibrium discharge, right? And it is all unit is also mentioned, meter cube per second. Any approach from your side? You can compute, you can tell me the values. See, there is no hard and fast formula or maybe concept which are working in these in such type of questions. Okay, just a kind of unitary methods, or maybe from the unit you can also approach. Okay, just for this case you are getting an idea that we want to compute equilibrium discharge, so unit will be in meter cube per second, right? Now how we can get it? So think in somewhat catchment scenario. Okay, so for the catchment scenario you should have some idea that yes, area is given, okay, and excess rainfall depth is given. So excess rainfall depth is nothing, it is just a direct runoff depth. Okay, so if you multiply area of the catchment with effective rainfall, or that is a direct runoff depth, runoff depth, you will get the total volume of water which can be stored in the catchment. Okay, once you got the idea that this much of volume have been stored, now if you divide it by t, that is a time, v by t. Okay, you know that equilibrium discharge, so it is a rate of change of volume. Okay, am I right? Am I right or wrong? dq equals dv by dt. You may have studied this in Darcy law or anywhere. So q equal to v by t, it is just a simple relation, and now you have to work it out. So here you need to calculate q, but keep in mind the units. Okay, so here a should be converted, it will be 270 into 10 to the power 6, am I right, meter square. And then it is mentioned here 3 hours, so it will be converted into seconds, so 60 into 60 into seconds. And what about 1 centimeter? So 1 centimeter will be 1 upon 100 in meter. Okay, so if we want to compute QE, so it will be volume divided by time. So total volume if you want to compute, then it will be further divided into area of the catchment and excess rainfall depth. So I am writing it at D and divided by time. Okay, meanwhile I am solving this, you can solve it and directly tell me the value. Okay, just solving it. So we are having the areas 270 into 10 to the power 6, then it will be multiplied by sorry, I guess don't confuse with this, there is a d duration it is mentioned, and if I am talking about runoff depth, I am writing it as ER. Okay, don't confuse with this. So ER here I am writing, so it will be 1 upon 100. Okay, and in total it will be divided again by 3 hours, so it will be converted into 60 into 60. Okay, so I guess 4 zeros are there, it will get cancelled out. So 270 into 10 to the power 2 divided by 3 to 6 into 6. ये 3 9s are 27, right?
250 meter cube per second.
That's good, ma'am. Yeah.
Why we written 1 by 100?
Because it was in 1 centimeter now. So in order to compute, in order to convert all units in meters, okay, so ER was converted to 1 upon 100, so it is now in meters now.
And if
right?
it was rather scoring medical frequency, okay. But I didn't understand.
You didn't understand?
Okay, I got it. Effective rainfall is 1 centimeter.
Yes, yes, yes. 1 centimeter. So
Hmm.
it has
Or
got.
unit hydrograph.
Yeah, yeah.
Okay, okay, okay.
Now you can have more idea
Hmm.
from this slide. You can get. Uh, Balamurgan got the answer or not?
Yeah, he got it.
Okay, he got it, and ma'am also got the answer. Good, and you were near to the answer only. That's good thing.
Hmm.
Okay, should I move ahead now?
Yes.
Okay. Okay, so the next question here is related to runoff coefficients. Okay, runoff coefficients. You will be like why this runoff coefficient is important, because these coefficients like account the changes in the land surface. Okay, I guess, I hope you may be knowing one word, that is Manning's coefficient. That is was one of the
Hmm.
parameter which uh,
Yeah.
represent the variability, I guess, that is in the river bank or along the channel. Okay,
Roughness.
roughness. Yes,
Measure
yes,
of
that is the word,
roughness.
right? Roughness. Yes. So, in the similar fashion, runoff coefficient is introduced in order to take care of catchment, maybe what are the flows going on at different area. So, if I'm saying that here forest cover is more, and soil, I can if I talk about the urbanization, I'm saying that forest is more in this case. Second case, you can say urbanization is more. Okay, and in the third case, you can say there is some more changes, or maybe agricultural land is there. So just this kind of variation, spatial variation is involved here. So when we try to model our output from input, input is what? Rainfall is coming. Okay, you can say that rainfall may be constant for the entire region. I can assume it, but due to the influence of these LULC pattern, I may have different runoff from all these sections, right? In order to incorporate this spatial variability, or maybe effect of land surface. Okay, so these coefficients are important. So here it, it is mentioned is there that there is one catchment, and you can assume it as 100%, so that could be regarded as 1. Now this catchment is divided in three major sectors: 25%, 30%, and 45%. So this is 25%, and this is somewhat 30%, and remaining part is 45%. Is it coming to 100?
Yes.
Okay, that's good. Okay, now for these areas, coefficient, runoff coefficient is also mentioned. So you can say C1, then there is C2, then there is C3. Okay, so we have to find out the equivalent runoff coefficient. Equivalent runoff coefficient. So equivalent runoff coefficient will be what? It will be a weighted
Weighted
area
average.
average. Yes, right. Weighted average will be, we have to compute. So now if you got this, you can compute the values directly. Okay. So here I'm writing as A1 I'm having 0.25, A2 I'm having value of 0.30, then A3 I'm having value of 0.45. For this, for the all these areas, I'm having runoff coefficient. So C1 is 0.40, C2 is 0.50, then C3 is 0.60. Now if I want to compute equivalent runoff coefficient, so it will be K1 A1 plus K2 A2 plus K3
Three,
A3,
three.
divided by, just I mentioned, area should be total. So E1, E2 plus E3. Now tell me the value, final value. I'm just writing 40, 0.25. It will be added by Q2. So here Q2 is what? I guess don't take his K1. It will be C1, C2. That will be good to understand. C1, C2.
No, no, it's okay.
Yeah.
Divided by 100.
Divided by 100. Yes. So divided by not 100, it will be coming up 1.
Correct, correct,
Right.
correct, correct.
So 0. Tell me the answer.
25 into 0.4
P0
into
plus 0.60 into
plus
0.25.
10. Yeah, it's 0.52.
Okay, you are getting 0.52. Ma'am, what about you?
With 0.49. I don't know whether I made a mistake in this.
How much?
0.49 I get. But I'm not using a calculator. I'm
Then
calculating my mobile.
okay, okay.
Uh,
Nearby you are
maybe
getting. Okay.
maybe the truncation error or something.
That's good. Okay, and Ashish, tell me what about Balamurgan?
One second, let me check.
How much?
Yeah, he says 0.52.
0.52. That's good. Okay. So the correct answer will be 0.52 only. You can see from this picture. So direct this formula have been used. Okay, and we are getting the value k equals 0.52. Okay, moving to the next question. So question here is 6R unit hydrograph of a catchment having an area of 1200 kilometers square can be approximated as a triangular unit hydrograph with a base period of 8 days. So I'm just plotting here a triangle. Okay, and triangle with what? It already mentioned this is the base period, right? So base period will be how much days? 8 days. And area of the catchment, it mentioned that 1200 kilometer square. Good. Then this hydrograph is having a duration of 6 hours. Okay, 6-hour rainfall is happening continuously, and we are getting effective rainfall value of 1 centimeter. Now in the second scenario, the peak flow in the DRH of this basin produced by an ER of 5 centimeter in 6 hour equals. So now it is asking about Q peak. So we are concerned to find out this value. Okay, don't confuse. We want to compute this value. So QP we want, but provided what they have provided, they want us to compute QP for ER of 5 centimeter that is happening at the rate of 6 hours. Okay, so firstly try to compute QP for this case, and then we at the last what we will do, we will multiply it by 5 centimeter, like in the previous question we already did this task. Okay, so for getting this QP, what you will do, V by T, right? But here keep in mind this time will be a base period. Okay, whenever we are computing the volume, we always take area under the triangular unit hydrograph. Okay, so here volume will be what? Half into 8 days into, I am assuming it as peak discharge. I am writing as it like in words only, peak discharge. Now you got the area, entire volume you got.
Hmm.
Okay, And this volume will be how much? This volume will be equivalent to area of the catchment into what?
दो मिनट
If I am saying that volume I am computing, so volume will be equivalent to how much? It will be equivalent to area into effective, that is direct runoff depth now. Area into direct runoff depth.
तो 1 centimeter.
Yes, 1 centimeter. Convert this unit, and you already have area. You already have all these other parameters. Now compute QP, and once you compute QP, multiply it with 5 centimeter. Now at that case you will get QP for 5 centimeter of what? You will get a that will be a DRH, direct runoff hydrograph. It won't be a unit hydrograph now. Anyone is joining? Anyone is trying to join? Okay. Okay. So Ashish, tell me how much value you are getting? QP.
QP, we need to multiply half by into 8 days into peak discharge.
Right.
0.5
Don't
in
forget to equate with the other one. Area of the catchment multiplied by
1
direct
centimeter.
runoff depth.
We need to QP is peak discharge, na?
Yes, yes, yes. Peak discharge. We want to compute QP.
Okay, got it.
Firstly, in first case, we have to, from first case, utilizing all the input data that we have to compute the peak discharge. Once we get the peak discharge, the other scenario is based on that same basin. So there won't be any change. We will just only multiply our desired effective rainfall, and we will ultimately get the DRH, direct runoff hydrograph, peak of that DRH. Keep in mind.
So 300 into 10 to the power 6.
How much? How much?
300 into 10 to the power 6.
300 into 10 to the power 6 you are getting. Have you taken care of all the units? Like days should be converted into seconds.
No. So I did
No. It won't work now then. How it work?
Yes,
Because
8 into
QP
24.
will definitely it will come
Correct.
in meter cube per second.
4 into 24. Okay, we need to convert 1 minute. Yes, correct.
Also don't forget to convert 1 centimeter also. 1 centimeter it will be converted into 0.01 meters, because this is an effective rainfall.
So 1200.
Ma'am, are you getting the things?
I'm working. I was just a little slow. I'm just calculating now.
Yeah, no issue, ma'am. No problem.
34.7 something.
Yes, you are getting QP of somewhat around 34.7
7 meter cube per second. 7.2.
meter cube per second. Okay, this is from Ashish. That's good. Ashish, am I writing your correct name?
My name is, yes, correct. Absolutely correct.
Oh,
Double A.
good. Okay. Tell me if Balamurgan got the answer.
1 minute. I'll check. Balamurgan says it is 173.611 meter cube per second.
Final answer, he's saying.
He is saying maybe final answer.
Okay. So Balamurgan is
Uh,
saying.
Excuse me, in between I missed. Could you please repeat the concept I missed in between? So, discharge, you divide the volume by time. So, you have to multiply it by 8 because it is for 8 days, right? Can you
Ma'am,
please repeat?
keep in mind actually what we are trying to do is that we want to compute QP, right? But
Yes.
what we are doing here, we are equating the, like we are using the simple principle, that is volume equals area of the catchment into direct runoff.
Effective rainfall.
Yes,
Effective rainfall
yes,
depth.
yes. ER you can write. Yes. So you have to firstly determine the total volume of water in the catchment. Okay. This is a simple
Yeah.
thing we are using. Volume equals area into effective rainfall.
Okay,
Now,
I did that.
when how you will calculate the total volume of this water, total volume of
Oh,
water,
it's
just taking the
okay.
area of this entire triangle.
Yeah, yeah.
So half
Okay,
into 8
okay, okay.
is into
Right,
Q.
right, right.
It will be a peak. Take peak as any parameter, unknown parameter, QP.
Yes, yes, yes.
Yeah, it's 34.72, and then we multiply it by 5. We got the answer.
Yes, good. So 173.6 will be a final answer. Okay.
Mhm.
Ma'am, I hope you can see this slide. From this you
Yeah,
can
yeah, yeah.
match your
I
results
just
also.
area of the triangle was the volume of water in the catchment.
Yeah.
From that you got it. Okay, okay, fine.
Okay.
Understood. Thank you, thank you.
Yeah. Okay, moving to the next question. So it's a bit theoretical, but keep in mind before replying to the answer, keep your concept ready. It is having some assumption in this question. Okay. So question here is volume of direct runoff generated from a 6-hour unit hydrograph for the same watershed during the month of January and July. Okay. So the options are as follows. Now tell me what will the answer. Direct runoff generated from 6-hour unit hydrograph for the same watershed. Area is same. At one time they are plotting this unit hydrograph for January, and then again they are plotting for July month. Now inferences we have to make. So inferences should be based on it won't be a random answer. Okay, there should be some assumption. Any idea you are getting? Like it is having only simple variable, that is time. You can observe it in a clear way. Don't you notice that only the months are varying, right? Ashish,
Yes.
only months are varying, na?
Hmm.
Yes. So based on that month, we have to make inferences. But before starting the session, maybe one question was there which was representing one assumption, that is a time invariance.
So it should be the same, will be the same.
Yes, that the thing I just want you all to keep in mind. This was just a simple and tricky based on the assumptions only. So just for your information, it is mentioned here. Look at this line, time invariance. So DRH for a given ER in the catchment is always same irrespective of when it occurs. Okay, when it occurs, that means whatever the month may be there, it won't change, it will remain same. Okay, clear to all?
Yes, clear.
Okay. Okay, coming to the question, I guess two more questions are there. This one, this is last second, then there will be one more question. So, question here is related to flood hydrograph. So, flood hydrograph, how we will be getting? We are getting just by adding the DRH with base flow. DRH will be added to base flow and we will be getting flood hydrograph. So a question here is the peak of flood hydrograph due to 3 hour duration in an isolated storm is 270 meter cube per second. So we are provided with QP, that is a peak discharge, 270 meter cube per second. Then tell me the additional information that we have. We have duration, right?
Yes.
So duration is how much? 3 hours. Then
3
what
hours.
we have? We have effective rainfall. We have effective rainfall of 1 centimeter. No.
Hmm.
We don't have idea about that.
Hmm.
Anything mentioned in these two lines? Can you figure it out? UH is mentioned anywhere?
Peak of the flood.
No. So we can't use this, right?
Yes.
Now we are moving ahead with further information. There is one more thing mentioned, that total depth of rainfall is 5.9 centimeter. Now you can say that total depth of rainfall which happened there is 5.9. So total rainfall depth is given here 5.9 centimeter. Also average infiltration it is mentioned. So average infiltration rate is given. Keep in mind. Okay. Now tell me the effective rainfall. Compute it fast. Okay, and tell me the value. 0.3 centimeter per hour it is mentioned. And you already know that how much was the duration of rainfall. It was at the rate of 3 hours.
3
now
hours.
compute this value. 0.3 into 3, that will be somewhat 0.9, right?
0.9, yeah, it's 0.9.
0.9 centimeter. Now tell me the effective rainfall value. Effective rainfall, ER will be total rainfall minus
Precipitation.
yes, no, total rainfall minus average
Infiltration.
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 Yes.
So
Now
infiltration we have to multiply 0.3 into 3.
so yes, average infiltration we already got na 0.9 centimeter.
Yes.
Now subtract this value. Total rainfall was what? It was about 5.9. So 5.9 minus 0.9, that will coming up 5 centimeters. So we got the idea that ER, how much ER was there for this case. So ER was nearly to 5. Now moving to the next part. What they want us to compute. So estimate the peak of 3 hour unit hydrograph of this catchment. Simple thing is there. Now again the proportionality will work here, that you already do. Okay, so here QP, whatever the QP value is given, keep in mind QP value is given. This is for ER having how much ER was there
5
in order to
centimeter.
generate this,
5 centimeter.
Yes, 5 centimeter. Good. And now they want us to compute QP for how much?
1 minute. For the
For ER equals
1 minute.
see, duration is same here. Only one thing is varying, only the effective rainfall. In the earlier case, 270 meter cube per second was generated due to the effect of effective rainfall of 5 centimeter. But now they want us to compute QP at what? ER equals 1 centimeter.
Okay, sorry, I got it. One
Yes.
for unit hydrograph.
Keep
Okay.
the things ready in your mind.
Yeah.
We all,
Correct.
if you are having idea, if word is mentioned unit hydrograph,
Mhm.
directly take out two values. Firstly, take out the D. D is how much? 3R. Then keep mind in this unit also. So we will write it as ER equals 1 centimeter. These two values should be taken out from this. At the
So it
beginning
is
you should take it out. So now ER should be 1 centimeter. Now for this case you have to compute this QP. Now tell me the value.
54,
What?
54 meter cube per second.
Okay, so you are saying QP, how much it is coming? 54 meter cube per second.
Yeah.
Let's see the explanation. 54 you are getting, it is coming approximately 550 meter cube per second. I don't know, maybe calculation may be wrong, you may be right. What is happening here?
You have substituted 250 instead of 270.
Yeah.
That's the mistake.
Okay, that is a mistake, right? Good. Okay, so I guess Balamurgan also got it. Ashish, you can confirm.
Yeah. Yeah, he got 50, 50 meter cube per second.
50 only.
Yeah. Maybe he also substituted 250.
How much was there? No, 270.
No, you correct. You correct. He minus 20 also.
Okay.
Base flow. We have to minus base
Yes,
flow
we are
also.
having a
So you
base
are
flow
right,
also.
we are wrong.
Yeah, exactly.
Yes, it was given. Yes. Constant base flow was there. Okay, it got missed from my side also. Good.
We have to minus base flow
Nice
also.
observation from Balamurugan. Sorry for my words. Good effort. I am happy that he noticed these things. Good. Okay, so Ashish, we have to make modification. We have to subtract.
Yes,
Okay.
yes. I got it.
270 minus 20, then we will come up with 250.
50, yes.
Ma'am, you got it?
Yeah, I
Okay.
got it.
Ashish, shall I move ahead?
Yes.
Okay.
Yes.
Now this is the last question of today's session. So the above part, what are you seeing? These entire information that is already matched with the previous question itself.
Yes.
So whatever the
correct.
inputs you are getting, that is same. Inputs are same. Just the change here is what? We have to compute the base width. There should be some change in the base width when we are considering it as triangular in shape. So base width, if it is mentioned that base width we have to take, then definitely again as per my opinion, the thing should be the things should click in your mind, that should be like volume equivalent to area of the catchment
Into
into,
depth.
yes,
Depth.
rainfall depth, effective rainfall depth, ER. So use this information and you can compute it. Now it's your effort, that how you are taking these values. Also it is mentioned that triangular in shape, definitely. Why it is mentioned? Because this
Half
question
base into altitude.
wants us to compute volume by taking a area of the triangle. So that is why it is stressing to this point. Okay, so volume you can compute it. So half into
Base into altitude.
base we don't know, so we are assuming at B into what? Into the QP. So in the previous question, what was QP? Okay, so QP was 270 minus 20, so it will be 250 only, right? 250 meter cube per second, and again area multiplied by effective rainfall. So effective rainfall will be how much? They want us to compute for effective rainfall of 1 centimeter, right? Because 3 are unit hydrograph, they want the base width for this. So effective rainfall will be how much? 1 centimeter, and area 567 kilometer square. Convert it into meter square. 567 into 10 to the power of 6 meter square into ER. ER is 1 centimeter. Now convert this. 1 centimeter, it will be coming like 0.01 meters. Okay, now take out this b. B will be the answer, and b will be in meters also. Unit will be meters. Try to solve this.
1 minute. I'll do that. Okay.
Anyone got the answer?
The
Forty-five
Balamur,
thousand three sixty.
Okay. What b value? B, how much you are getting?
Balamur get 63 hours.
63 hours. Yes. Ma'am, what is the unit you are getting? Oh, sorry. It was base width na? No. It won't be in meters. Sorry. Actually, I missed this. It will be definitely, you will be getting, initially you will be getting in seconds. Then it will be converted to hours. Okay. I have not noticed this. Base width in simple terms.
12.6. Is it 12.6?
12.6. Okay. We will check it. 12.6 hours. Then again base width is 63 hours. Then Ashish, from your side, any answer? Ashish, any reply?
You can move forward. I'll do it.
Okay, so here the answer is 63 hours. Okay, now we will look into, ma'am,
22.
from this look into this slide and kindly find out where you were wrong, why you were getting 13.2 hours in.
Okay. I'll correct. Thank you.
So what was wrong, ma'am? Can you tell me what you have taken wrong value, where you have taken wrong value? See this line, volume represented by area of UH, it will be equivalent to volume of 1 centimeter depth over the catchment. So area of UH in the sense what? It is representing a volume. So how much volume we are getting? Half into multiplied by B multiplied by 60 into 60, okay, into 50 in the sense why it won't be a 50, I guess it will be 5. There may be a wait a minute, we are plotting.
The area of catchment is
No,
1
it
centimeter
will
depth,
be
and bottom is
250.
time, na? Time. So half base 60 is correct.
Yes, then it
And
will be a peak, so 250 it will be, right? Because we are having the discharge 270, so 270 will be subtracted by base flow, so it will come up how much? It will come up 250, right?
250.
Because area will be what? How we are computing this? So Q is here, okay, so Q is here, B is here, and area we want to compute, so half B into Q. Good.
is
So
equal to
okay, this will be equivalent to area. So area is this much and effective rainfall is this much. Okay.
correct. So we say 0.5 into 60, 60, 50. 0.5 into 60, 60 into 50.
Ma'am, do you got this point that why we are multiplying 60 by 60?
Yeah, I
Yeah,
got
9 into
it
10 to the
because
power 4 is correct.
yeah,
Ah, that's good. Okay.
But if we multiply it by 50, then only we get 9 into 10 to the power 4.
Okay, wait a minute. If we are using 50,
Yes.
then Balamurgan, where we are going wrong?
He says that 50 meter cube per hour per second is unit hydrograph.
Okay, unit hydrograph. If the area of catchment 3R unit hydrograph area we also got this. Then we want Q.
250 is 5 centimeter rainfall, he says.
250.
Is for 5 centimeter rainfall.
Okay. Okay, got it. Okay, it is
Okay, okay.
utilizing
Yeah,
this
yeah, yeah.
this part. Okay, got it. Yeah, that was a mistake. Good, nice
We
observation.
have to divide it to get for unit hydrograph.
Yes. So it will be 50 only.
Yeah, 50 only.
Good.
Correct.
Nice observation. Good. Sometimes while solving it in slides, I also got stuck, like considering some other aspect or maybe other factors. So yes, definitely a nice observation from Balamurgan. Good, good to see. So ma'am, I hope now it is clear to you also.
yeah, it's clear. Thank you.
Okay. I can erase it so that it will be
Yeah.
understood when other people will watch it out. Okay. Okay then. So I guess this is the last slide. So now I'm stopping this presentation and okay. So okay, Balamurgan, good. Nice to see your efforts. So okay, we will meet in the next session. And if you all are like any queries there from you all, we can discuss in the beginning of session. Okay, so while
Hmm.
getting any kind of difficulty whilst you are solving the problem assignments, we can discuss it, or maybe we can discuss some other aspect also. It doesn't mean that we should stuck with what we are discussing right now. We could discuss with other aspects. So definitely I will be happy if we are discussing some other topics, like what is going in the trend, or you are going wherever you are working, you are getting anything. I can it will be a learning aspect for me also, right?
Yeah, so then next, maybe next to next week, I am preparing one report for draft report for my client, and I will share it with you.
Yeah,
So
that's
we
good.
can discuss that one.
Yes, that's fantastic.
Yeah.
I will be happy to say this. Yeah.
We are doing hydrology study for one of the solar project to be located in Maharashtra.
Okay, that's good. Yeah, good.
We are doing that one, and
Good, Ashish. Good,
we'll
good.
prepare and we'll share.
Yes, sure. Okay then. So I'm now stopping this presentation.
Thank you, sir. Thank you. I
Yeah.
got that point 5 to I had made a mistake in one number. Then I got
Okay.
problem 13. I had
Yes.
made a mistake. And I corrected.
These
Thanks.
questions are more mathematical rather than some conceptual. These are
Yes.
conceptual. Yes.
Right. Exactly. Okay.
Okay,
So
thank you
we will
very
meet
much.
in the next session. Till then,
Sure.
bye. Take care.
Okay, bye.
Yep.
Thank you very much. Thank you.
Yep.